Alright, today we're going to talk about the push-pull power amp. So it uses two tubes. So it can be class A, AB, or B. In class A, both tubes have plate currents all the time. In class B, they have current half of the time. So one tube amplifies one half of the signal and the other tube amplifies the other half. So if you want high fidelity, you would run class A. If you want a more efficient amp, you would use class B. But here I'm focusing on class A. So what's the advantage of the push-pull configuration? You get less distortion, especially the even harmonics, in particular the second harmonics, because you have a cancellation effect. Similarly, you get less hum. Again, it's a cancellation effect of the two amplified signals. When you add them to each other, there is a cancellation happening, and you usually have more power. You have more power with the two tubes used as a push-pull amp than if you were using the two tubes as single-ended. So one tube amplifier, like a two-stage amplifier. You have more power because of that less distortion, so you can push them harder. And also the other advantage is that you can use smaller tubes and you can use smaller B+. So those are the advantages of the push-pull power amp. So now let's look into the details of how it works. Okay, so this is your typical schematics. So this is here on the left. This is the input signal. Okay, let's say it's coming from your guitar or whatever. And let's assume that we have a phase splitter here. And this is a whole subject by itself. So it's the phase splitter splits the input signal into two parts. And they both have the same amplitude. They are just inverted with respect to each other. So this one is the same as input, and this one is 180 out of phase. And this is the push-pull configuration, the two tubes. So you have a tube 1 at the top, tube 2 at the bottom. But other than that, you set it up like a regular amplifier. So here you have the cathode bias. So you have your cathode resistor and the bypass capacitor connected to the cathode. You have your plate. So that's going to be your output. Okay, so, and then the same thing on the bottom. So you have your other tube. Same configuration, just mirrored. Assume there's a mirror here and it's just mirrored. And the output goes into the two ends of your output transformer, which is center tapped. And at the tap you have the B+. And here in red I'm showing the positive plate current. So in tube 1 and in tube 2. So that's the convention for the positive. So it goes from B+ to the plate and this way. Then through the tube and then ground. Same thing here, mirrored. So it goes from here like this. So that's your convention. Because we want to see if this, what happens at for the voltages here at the primary, do they add up to each other or do they cancel out each other? Because at the end, of course, we want this type of signal, the amplified signal. So this is the output. So how do you get that? And I'll talk about that in the next one. Yeah, so the question is, how are the voltages adding up in the primary? So this voltage here and that voltage here in this half of the winding. Okay, so let's look into that. So this is a bit tricky, but let's make it as painless as possible. Okay, so here. So when this voltage, the input voltage, goes through that tube 1, the plate current here, is in phase with this one. Same thing here. The plate current here is in phase with this one, as opposed to the plate voltage, which is inverted. Okay, so, but the plate current and this one are in phase. Plate current and this one are in phase. Plate current and this one are in phase. That's important. Okay, so now this is the plate current tube 1. This is the plate current tube 2. So they are inverted. And here I'm only focusing on the AC part. So here I'm just blowing up the primary of the transformer. And here, this is again my positive plate current for tube 1. This is my positive plate current for tube 2. I didn't draw the tubes, but tube 1 is up here, tube 2 is up there. It's basically the same picture as before, just blown up near the primary. So V1 is my positive voltage. So I goes down, so positive V1 is going up. Same thing here, mirrored. I goes up, V2 goes down for the positive. So this is just a convention. And we are interested in that the voltage across both ends of the primary winding. We want those guys to add up, not to cancel each other. So here in this case we have V equal V1 minus V2. Okay. Okay. So now we have to look into how the changes in the plate current induce a voltage in the inductor. Remember, this is not a resistance, so we cannot use the regular stuff. The voltage here is going to be induced by the changes in the plate current. Okay, and here I give the formula V equal L, which is the inductance, times di over dt. So it's the variation of the current that induce the voltage. So here let's focus on the quarter cycle. So here the plate current is increasing, and here the plate current is decreasing. So let's look at the tube 1, V1. What's V1? Well, if you just apply this formula, you can easily tell that this is the shape of that waveform, that first quarter. It's maximum, and then it goes to 0. Okay, so it's coming from variation. Di is just a variation. So at the beginning, the slope is maximum, so that's why you get the maximum here. And here, the slope is minimum, 0. So you get the crossing here, 0. And if you remember your electronics courses, inductor is always 90 degrees out of phase with the current. So that's why you get this for V1, and V2 is similar. V2 is similar, except it's going towards the negative. So the V2 is going to be here is going to be maximum here, so maximum here, but except that it's negative now, negative value, and here it's minimum 0, so you get the 0 crossing here. And if you want, I'm not going to go through all the quarter cycles, but that's how it looks like. I should have probably gone the rest, but you get the idea. So this is V1, this is V2 for that first quarter cycle. So if you, and remember that V is equal to V1 minus V2. And as you can see, when you negate this signal, it becomes here this signal, and it adds up to this one. So you get, twice. So you get the amplified signal, and the important part is that the two parts add to each other. They don't cancel each other. So you can do this for the next quarter cycle, the third quarter cycle, the fourth quarter cycle. You get the same idea. So I'm not going to go through that. So that's basically how it works. So, and then the voltage at the primary, it goes through the output transformer, and we talked about that before, and this powers your speaker. Everything relies on this, realizing that this happens, that those two voltages add up to each other. They don't cancel each other. So that's, and this is all due to the center tap. Okay. Now, before we had a phase splitter, which I'm probably going to talk about in a different video. We have a phase splitter, we get the two signals. But you don't have to do that. You don't need to split. You can do it directly. You can have a push-pull amplifier that doesn't need a phase splitter. And let's see if I can explain that. This one is also so it's called a cathode coupled push-pull amplifier. So okay, the input is here. Here you have your coupling capacitor as usual, C1R1. So this is your input here. So I'm showing at the sine wave. Tube 1, tube 2. Again, you have your transformer with the center tap, and then you have your output where the speaker is. But what's important to look into is the phase change, how the phases change as you go along the circuit. So let's look into tube 1, how it's set up. It's a usual setup. You have the plate here, grid, cathode, and you have your cathode bias resistor here. So it's the usual setup. And actually, that cathode bias is common to both tubes. So that's tube 2. And the interesting part is that the grid, usually the signal comes into the grid. But here, the grid is grounded. So that's different. Yeah, the B plus is here, not... Okay, so here you have the first amplifier. This is the usual thing happen. You get the plate voltage. The plate voltage is out of phase. So you have a 180 here. Okay, so you have 180 here. So that's your signal, the plate voltage. So this is the output of your tube 1, 180 out of phase. Now let's look what happens here. So here the input, as we know, the input signal and the plate current in that first tube are in phase. So that causes a voltage drop across R2, and that voltage drop is in phase with the plate current in tube 1. And since the plate current in tube 1 is in phase with the input, this voltage here is in phase with the input. So we have a 0 phase difference here. And now we are going into tube 2. So basically the signal is not applied to the grid, it's actually applied to the cathode. And what I'm saying is that the phase difference between the input signal and the output, the output voltage, which is the plate voltage of tube 2, what I'm saying is that there's no phase difference. No phase difference. So the question is why? So why do we have no phase difference here? So this is the cathode voltage. Okay, so if we go back to that picture, this is the cathode voltage here, so it's this way. And the grid voltage here, which is 0. And we saw that the grid was grounded, so that's correct. And with this kind of grid to cathode voltage, this is the plate current you're gonna get in tube 2. This is the plate current for tube 2. And the plate current is gonna be 180. It's gonna be 180 out of phase with the input, so meaning that is inverted with respect to the input. And this is because the signal is actually on the cathode. So when you apply the signal on the grid, there's no inversion, but when you apply the signal on the cathode, you have the inversion. That's the easiest way to remember this. Okay, so signal to grid, no inversion. But if you put the signal on the cathode, you get inversion. So the plate current is inverted with respect to the K voltage. And yeah, you have to remember that for whatever amplifier you look into, you have to remember that the plate voltage is always 180 degrees out of phase with the plate current. That's always true. So the plate voltage is 180 out of phase with respect to this one. So now it's actually in phase with respect to the K voltage. Okay, so this is in phase with this voltage here. And by the way, it's not zero here. It's whatever DC level. It's not zero. Zero might be here, let's say. Same here. It's the DC voltage here. Because here you have it's positive here. So let's say +3 because of the voltage drop across R2. Because of that voltage drop here. Because of the R2. So you have a positive DC voltage at the cathode. So it's easy to see because as you go up here, the plate current is going to go down. So it's going down. And as you go, because the cathode to grid voltage increases, so the plate current is going to decrease. If the cathode to grid voltage increases, the plate current is going to decrease. That's the take. That's what you have to remember. And here, so here the grid or the cathode to grid voltage decreases. It means that the plate current is going to increase. So you're going to be here. So here corresponds to there. So that's why the plate current is inverted. So now if I go back here, so this is the voltage of the cathode, and here you have the output plate voltage, which is in phase. So now you have a 180 out of phase at the top and in phase at the bottom. So you end up with exactly the same situation as this. Exactly the same situation. And basically here you would have this and this one, the voltage here, and this one would be like this. Exactly the same situation. Yeah, so then again it goes through the transformer and then to your speaker. Exactly the same. And what I wanted to say is that this circuit is actually used in most cases as the input to a true push-pull amplifier. So this acts as a phase splitter, if you will. You get the two phases here, and then you don't put the transformer here, the output transformer here. You go through another pair of tubes, and then the output transformer. So this is only used to get the two phases, and then you have the push-pull after that. So I think I'm going to stop here. I think I've rambled enough about this. Okay, so I'll see you around. Bye.